I'm very grateful that you invited me to this conference, this workshop. I think it is very important to do these things once in a while. I'm a physicist, and I'm going to talk about something that is mathematics, so I will go very lightly on some things that have many subtleties and many details that I will not tell you about. But I wanted to make a general talk so everybody could understand what is the main idea, to relate quantum logics and fuzzy logics. We will define both of them and we'll see what is the relationship. First of all, I will start with explaining what is the classical logic, what are multi-valued logics, and what are fuzzy sets. Then we will study the quantum logics in general, and in particular, we will concentrate in the logics of quantum mechanics. It's not the same as a quantum logic. It's a particular quantum logic that is the Birkhoff-von Neumann logic or standard logic. Then we will see the axiomatic approach to quantum mechanics by McKay. Also, I will go very lightly because this is a very profound subject. Then we will see the theorem that relates fuzzy logics and quantum logics. And if I have time, I will show you a couple of examples that we did in our paper, the fuzzy bit, so the qubit, and two entangled qubits. We also did the Q-thread is called Q-thread. But that was more involved, and I will not have time to talk about that. So, what is classical logic? Is the logic of propositions of this type. In the state S of the system, the observable A has a value, the observable F has a value in the subset E of the real numbers. So we have to have a set of states. In this set of states will be the points in phase space. Unobservable, a set of observables that will be real functions of phase space. And for the sets of the real numbers, for technical reasons, we will choose Borel subsets. So the proposition above will be true if the system is in a state that belongs to F-1 of E, and false otherwise. So propositional logic, the proposition that I stated there, can be translated into a subset of phase space. And the propositional logic, the classical logic of a system, can be mapped to the Boolean algebra of subsets of the phase space. Here the connectors and or correspond to intersection and union, the negation is the complementation, and the implication is the inclusion. So we have a complete map from one logic to the Boolean algebra of subsets of phase space. So you see the propositions of classical mechanics can be true or false. It's a logic that is two-valued, but there are many situations in which many-valued logic it is useful to have. I present here, for example, the simplest example, that is a three-valued logic that has three possible values: true, unknown, and false. And you can imagine that this kind of situation can be present in many situations of real life. Then we have a generalized tables of truth for the operators, the operators and or, and also the negation. These are generalized tables of truth, and we can also increase the number of values. We can have n-valued logic, but if we somehow want to relate this to quantum mechanics, we see that these many-valued logics are too simple. We want something that resembles probability, so the type of logic that we will be interested in is where truthfulness has a value that can vary continuously from 0 to 1, in the interval 0, 1. So, well, this is the kind of logic that we will think about it. We have a continuous parameter of truthfulness, and it was shown by Gilles that the same relation that exists between classical logics and set theory can be established between this type of logic and fuzzy sets. What is a fuzzy set? So you need to have first a set that is called the universe of discourse, and then you will consider subsets, fuzzy subsets of the universe of discourse that are given just by a function that maps U to the interval 0, 1. So we will interpret 0 as non-membership, a complete non-membership to the fuzzy set, and 1 as the full membership. And in between, we can have any degree of membership. A crisp set, in this case, will be a function that is the characteristic function of the set. So these are just ideas, but what can have this to do with quantum mechanics? Because quantum mechanics is something more than probability. We have amplitudes that are responsible for interference and for entanglement. So it is not enough saying I'm going to interpret fuzzy sets or crisp sets as classical or quantum mechanics. We need something else. And then I found funny this one. So let's go back to logics and let's see what is a quantum logic. A particular case of which will be the logic of quantum mechanics, that is the Birkhoff-von Neumann or standard logic. So quantum logic is a partially ordered subset. A partial order in a set is a binary relation that is reflexive, transitive, and antisymmetric. We will say that it is a poset, and an example of it is this whoops. What happened? This is, no, I'll make it.
I just want to put it back into.
Ah, okay. So what is the laser pointer? Ah, this one. So we have this diagram here that shows explicitly the partial ordering in the set of all subsets of a 3-element set. Okay, so you see that it's a partial ordering because not all the arrows are possible. Okay, some properties that have posets. If there exists an element such that is less or equal will be I will use for the binary relation. It doesn't mean that it is a numerical relation. So if there is an element that is less or equal than A for any A, then we will say that this element is the 0. We will call it the 0. And it is unique. If it exists, it's unique. The same happens for an element 1 that is bigger or equal than A for any A in A. And then if it exists, it is unique. And the same concept can be defined for any subset of A. Then they are called the meet of the subset S and the join of subset S. These also, if they exist, are unique. So now we will be adding properties to the poset in order to convert it into a logic. What is a lattice? Well, it's a poset such that 0 and 1 exist, and so do the meet and the join of any finite subset. Another requirement will be to have a map that is called the complementation. It's a map from the lattice L to L. It's bijective. It reverses the order, and it is involutive, and it is complementary in the sense that I'm going to call, sorry, I'm not being very... Okay, finally. I will say that this element is A orthogonal, although it has in principle nothing to do with orthogonality. But I will say it, that is orthogonal. So A meet with A orthogonal is equal to 0, A join with A orthogonal is equal to 1. So if X is less or equal than Y orthogonal, we will say that X is orthogonal to Y. More properties is what is an orthomodular lattice. It satisfies this law. No, yes. Come on. Sorry. Okay, it satisfies this relation that it looks complicated, but it is nothing but a generalization or a relaxation of the distributive property of the meet with respect to the join or to the join with respect to the meet. So lattices not necessarily have the orthomodular property, but the ones that are distributive are very few. So this is a generalization. And finally, we will say that an orthomodular lattice is sigma orthocomplete if for every countable subset of pairwise orthogonal elements, the join exists. Okay, so this is a logic. An orthomodular sigma orthocomplete lattice is a logic or a quantum logic. It is used, both terms are used. I think logic is more proper because the classical logic, the Boolean algebra of subsets of a set, is in this sense a quantum logic too. This is a quantum logic that satisfies the distributive property that, as we say, ensures the orthomodularity of the lattice. Okay, so we have defined what is a quantum logic. Let's see what is the logic of quantum mechanics. We consider a Hilbert space, God-given Hilbert space that possibly is infinite dimensional. And we let L be the set of all closed subspaces of H. Then there is, in this set, this a partial ordering that is given by the inclusion. The meet is the intersection, and the join is the sum of vector spaces, because the union of vector spaces is not a vector space again. So the complementation will be the orthogonal complement in the Hilbert space using the inner product. The orthomodular law, one can prove that it is satisfied, so L is a logic. If the Hilbert space is finite dimensional, one can replace the orthomodular law by this other law that is more restrictive, and you see that it resembles a bit more to the distributive property. But still, this logic, even for finite dimensional Hilbert spaces, is not distributive, and this is the main difference of the logic of quantum mechanics with respect to the logic of classical mechanics, of a classical system. If we speak about quantum mechanics, we have to say what is a state, and we have to say what is an observable. So I will give you the definition first, and then the justification, because the role they play in the standard logic. So a state in a logic is a probability measure on L. That is a map from the logic to the interval 0, 1 that satisfies these two properties. Rho of 1 is equal to 1, and for any sequence of pairwise orthogonal elements of L, rho of the join of all of them is equal to the sum of rho applied to each of them. So these are the standard properties that has a probability measure on any set. In particular to this, it has to be on the logic. So what happens in the standard logic? In the standard logic, let psi be a unit vector that represents a pure state in quantum mechanics, and P an orthogonal projector that represents a subspace or a closed subspace. It can be represented by its orthogonal projector. Then the map that sends P, no, that sends P to this quantity here, P psi bracket with psi. This is a probability measure on L. It is clear that it goes from 0 to 1, and it also that has the properties that any probability measure has. These are not the only probability measures. We can also take a linear convex combination of them, and then we will be in the case of having a mixed state. And a state that in finite dimensional case can be described with a density matrix. What is a theorem that is very profound and very difficult to prove is the theorem by Gleason that, in fact, in dimension bigger than 2, these are all the probability measures that you can have on a logic. States are in one-to-one correspondence with probability measures, and that's why we define a state on a logic in that way. What is an observable? An observable is an L-valued measure on R. This is a measure on R, but it takes values in the set of elements of the logic. So it has all the I don't want to read them, but it has the standard properties of a measure. If we go to the standard logic, these L-valued measures are projector valued measures, and we know that by the spectral theorem, there is a one-to-one correspondence with self-adjoint operators in the Hilbert space. So this is why an observable is defined in this way. Okay, so now we focus the problem from another point of view. We want to see the axiomatic approach to quantum mechanics by Mackay. Mackay, what did was to set a series of axioms that if they are satisfied, then we identify exactly the logic of quantum mechanics. You will see that it is not that easy, but it has its own problems. So it starts with having two abstract sets, the set that we call set of states and the set that we call set of observables that a priori have nothing to do with the states and observables that I define on a logic. This is two abstract sets, and then we consider the Borel sets on R. And then we have a probability, what we call a probability function, that it is P, and P of A rho E should be read as the probability that making a measurement of an observable A when the system is in a state rho, the probability that it takes value in the Borel set E is P of A rho E. So, okay. One thing that I wanted to mention is that measurement here is not defined. And this, up to now, nobody knows what is a measurement in quantum mechanics. It's what is called the problem of measurement. So we will leave it like that. These are the axioms, the first 5 axioms. If we keep fixed A and rho, then what remains of P is a probability distribution. That is, these are properties of P that will be axioms of quantum mechanics. Another axiom is that P distinguishes between A and another observable A prime, and distinguishes also between states. The third one defines what is f of A, if f is a function from the reals to the reals. The fourth one defines what are mixed states. And the fifth defines a poset with complementation. So we are arriving close to the formulation of the logic of a quantum system. So I will go fast on this, but it is important because these are the elements of the logic of quantum mechanics. There are observables that are called questions by Mackay, and are observables whose probabilities are concentrated on 0 and 1. For example, for an observable A and a Borel set E, the observable that gives 1 if the measurement gave a value on E, and 0 if not, is a question that will be denoted in this way. Will be denoted as QAE. These are plenty of them because we can have any couple of observables and Borel sets, and we can have plenty of questions. So now we consider a fixed state, and we consider a question, an arbitrary question, and we consider the probability that such question has the probability concentrated in 1. Okay, so this is the probability that the question gives 1 as an answer, and it will be, of course, a number that is between 0 and 1. Well, the functions S of Q for all states ρ determine Q, so they establish a partial ordering in the space of questions. So we have assigned to a state, we have assigned a function that establishes a partial ordering in the set of questions. In the set of questions, we have also an obvious complementation, that is m ρ of Q orthogonal is 1 minus m ρ of Q, and then the set of questions with these properties is a complemented poset. The axiom 5 states that if we have a sequence of pairwise orthogonal disjoint questions, so orthogonal is the same as disjoint in this case, so it means that m ρ of Qi is less or equal that 1 minus, is less or equal that the complement, m ρ of the complement of Qj, then the join of all the questions is also a question. And this can be for any countable sequence. Well, being fast here, because there are many things involved here, we can indeed say that the space of question is a logic with a set of the probability measures that are m ρ in S. That is, ordering, it means that the measures somehow define the order, are enough to define the ordering. But I don't enter into that. Okay, so then we have the sixth axiom that says that for any question-valued measure, there exists an observable A such that Q of E is just the question that we defined before, the question QAE. So this is the questions are related to observables in this way. Question value, you remember logic valued measures were observable, so here we have exactly the same. So then we arrive to axiom 7, and in the words of Mackay, this axiom has a rather different character from axioms 1 through 6. These all had some degree of physical naturalness and plausibility. Axiom 7 seems entirely ad hoc. And I would add, they had also some mathematical necessity. They were defined by mathematical necessity. So this is the axiom. The logic of questions is isomorphic to the logic of all closed subspace of a possibly infinite-dimensional Hilbert space. So then with axiom 7, we are back to standard logic. And this, up to now, nobody knows why the logic of the quantum mechanics is the logic of the von Neumann, the Birkhoff-von Neumann logic. Then axiom 8 says that if Q is a question different from 0, there exists at least one state for which m rho of Q is equal to 1. And this allows us to use Gleason's theorem that we mentioned before. It allows to prove that every measure on a question arises from a question. Any measure on the questions arises from a question, from a state. Sorry. And axiom 9 deals with the unitary temporal evolution of the system that we are not talking about it here. We are taking a picture of quantum mechanics in one precise instant of time. So now this looks that is very full, this transparency, but let's go one by one. These are definitions that correspond to fuzzy sets. We would say that two fuzzy sets of the same universe of discourse. Fuzzy set is, remember, the function from U to the interval 0, 1. If A is equal to B, then mu of A is equal mu of B for every x in U. A is inside B if mu of A of x is less or equal than mu B of x. Then we define a union. There are unions and intersections of fuzzy sets. There are defined many of them, but this is the one that will be useful for us. This is we call them the bold union and the bold intersection, and they are defined in this way. The bold union is the sum of the membership functions of the two sets, but if this sum gives a quantity that is bigger than 1, then we stay in 1, because we want that the bold union is still a membership function, so it has to go at most can take the value 1. The bold intersection, if you see, well, it has also a meaning, it has sense if we think in the intersection of crisp sets, and it has this value here. Is the maximum between these two quantities. The complementation is, as we saw before, is just mu of A orthogonal, let's say, is equal to 1 minus mu of A. And finally, we define the empty set as the membership function identically constant, identically equal to 0, and the universe of discourse itself has membership function constant, identically equal to 1. We will say that A and B are weakly disjoint in their bold intersection is equal to the empty set. So we have, you will see that this is the orthogonality condition. So this is the theorem of Picasse that I was mentioning to you before. It looks also very complicated, but it is not that much. And this is the theorem that puts in contact logics of fuzzy sets with quantum logics. So any logic with an ordering set of probability measures can be mapped isomorphically to a logic formed by a family of fuzzy subsets of S, let's call it LF of S, that satisfies the following properties. First, the empty set belongs to the family. If A belongs to the empty set, so does its complement. Given a countable family of fuzzy subsets that are inside this logic, and suppose that they are pairwise weakly disjoint, then the bold union of all of them belongs also to the logic. And finally, a technical condition that is obvious for crisp sets, but is not so for fuzzy sets, is that if A bold intersection with A is the empty set, then A is the empty set itself. And the same in the other way around. If we have a family of fuzzy subsets of a universe of discourse satisfying these four properties, then we have a map. Then we have a logic. If we have a family of subsets that satisfies those conditions, then we have a logic or a quantum logic in the sense that I was talking before. The orthocomplementation is the complementation of fuzzy sets, and the notion of orthogonality coincides with the weak disjointness. So, I don't know how much time. Okay. So, these are the set of measures, ordering measures, is given by elements of the universe U in this way. M rho of a fuzzy set A is equal to the membership function associated to A to the fuzzy set A applied to rho. Rho is an element of the universe of this course. So in this way, I have for every rho I have a measure on U. So this is the Picard's theorem, as I told you. So what does it mean? It means that any quantum logic can be put as a logic of fuzzy sets. And here it came the question why, if fuzzy sets seem to give me only the probability, why I can put also the Birkhoff-von Neumann logic in terms of fuzzy sets. Then, so if we look at it from the perspective of fuzzy sets, there is nothing that forces us to choose a logic whose universe of discourse is the density matrices of some Hilbert space. Here I am considering finite dimensional Hilbert spaces. So U is equal to the set of self-adjoint non-negative matrices of trace 1. And to compute the membership functions in terms of self-adjoint operators in this way. I can choose what are the fuzzy sets that I'm going to consider. So I can choose, once I have chosen the universe of discourse, I choose mu A of rho. Here what I have is the projector on the subspace defined by the observable A and the Borel set E. And this is the standard formula on quantum mechanics to extract the probability that a measurement of an observable A when the system is in a state rho gives me a number that is in the Borel subset of R E. So what we were curious about was to see how do they look, these experimental functions. So we took a few systems and then we computed these experimental functions. It is very easy to compute them for the fuzzy bit, for the Q bit. We call it fuzzy bit. And well, we are interested in computing these functions that are fixing A and fixing E. We call this function FAE, we call it experimental function. So we want to compute the experimental functions of the Q bit. They are functions that go from rho, from the set of states to the interval 0, 1. Okay, so we have H is C2 because we have a Q bit. S is the set of density matrices, and O is the set of self-adjoint operators. Density matrices are decomposed in terms of the Pauli matrices in this way. This vector that appears here is the block vector. And as you know, probably the block vector, the positivity condition forces the block vector to be inside a region that is a solid sphere of radius 1/2. This is called the block sphere, and the points that are on the surface of the sphere are pure states, while the ones that are in the interior are mixed states. The origin, you see, the origin means that rho is equal to 0, so we have rho proportional to the identity, so it is the maximally mixed state. So if we now take a self-adjoint operator, we can decompose it also in terms of the Pauli matrices, and then these are its real eigenvalues, where we have defined A as what would be the block vector of the matrix A. And with respect to these eigenvalues, we have 4 types of Borel sets. Borel sets that contain no eigenvalue, Borel sets that contain both eigenvalues, for which both, sorry. Borel sets that contain no eigenvalue, Borel sets that contain both eigenvalues, then the projectors are trivial, and then Borel sets that contain one of the eigenvalues, and then the projectors have this expression. These are the experimental functions. You can compute this as the trace of rho times PAE. And well, these are the experimental functions of the qubit. This is the orthogonality condition. Look, we want to see now how do they look, the orthogonal functions, the orthogonal experimental functions. We have that fa plus f of a prime should be less or equal than 1 because fa has to be less or equal than 1 minus fa prime. So this inequality should be satisfied, but this is the sum of the 2 experimental functions, and the only possibility, if this has to be true for all rho, is that A is equal to minus A prime. Okay, so this is the orthogonality condition. In terms of fuzzy sets, we have that the bold intersection is equal to 0. Because this is the maximum between these 2 quantities, it turns out that is the orthogonality condition. So the bold intersection and the bold union that we had defined it, and not in terms of the ordering, but we had made a definition of them, it corresponds to the orthogonality. The 0 value of this intersection corresponds to the orthogonality. Here, okay, it's fine. Don't say anything. On the other hand, if the fuzzy sets are orthogonal, you can compute the bold union, and that gives you 1. But this makes sense because now all the eigenvalues that we have is lambda plus and lambda minus, so we are considering all the eigenvalues. So naturally, if I sum both experimental functions, I have to obtain 1. This is a little issue, but it was made wrong. I mean, I read it wrong in the literature because there was some confusion. It is about the NOT gate. So I could take any of the observables, but I take sigma 3 because it's already, in terms of the eigenvalues, it's already diagonalized. And the NOT gate is this unitary transformation. Okay, sigma 1. What does it do? It flips the states of the basis, of the order basis. This flip transformation acts on density matrices in the usual way, and when we go to the experimental functions, it acts like this. You see that it changes the sign of this term and of this term, but it doesn't change the sign of this one. This is different from the complementation that changes the 3 signs. And this difference results to be very important because the NOT gate has a square root. It's, for example, so a square root is a gate that applied 2 times gives me the NOT gate. And the NOT gate has many square roots. This is only an example, but the complementation has any. So many people in the literature have taken the NOT gate as if it were the complementation, and then we show that this is not the case. I'm almost there, no? 10 minutes. Okay, so we have time to see the 2 entangled qubits. This computation is also easy, but it's a bit more complicated, only because we have a Hilbert space that is bigger, that is C2 times C2. And if we choose as a basis for the matrices, what are called the Dirac matrices, that are tensor products of the sigma matrices, then the density matrix can be written in terms of it. And the components R mu nu can be arranged in a matrix itself that, well, we have decomposed in terms of 2 vectors and 1 3x3 matrix. The meaning of these vectors is that if we trace out one of the systems, then we obtain the experimental functions or the density matrix of the other system, and vice versa. So R and S can be seen as the block vectors of the 2 independent separated systems. While R, we will give the name of correlation matrix, because it is telling me properties that are relevant for both subsystems. We will consider observables that are decomposable, because if you have a sum of matrices to compute or to put in relation the eigenvalues of the sum of 2 matrices in terms of the eigenvalues of each of the 2 matrices is a very complicated problem. So we choose to measure properties of one observable or properties of the other, properties of the one subsystem and properties of the other subsystem. That is what usually are in the experiments that we do with the spins, for example, is what we do. We measure properties of one of the subsystems. So then we have already computed what are the eigenvalues, what are the projectors, and it happens that for this case, in which the observable is decomposable, the eigenvalues are just the product of eigenvalues. So we have 4 possibilities here, and well, maybe some of them coincide, but let's suppose that they are different, and let's choose a Borel set that contains, for example, alpha plus plus. Then the projector is the tensor product of projectors. In these projectors, we computed them before. Then these are the experimental functions. Then after a bit of algebra, we arrive to this expression that is the experimental function. Then, okay, this is a probability, so we know because of the formalism of Hilbert spaces and quantum mechanics, we know that this is a probability, so it will satisfy these boundaries. So we can use this fact. But it is also possible, when restricting to pure states only, it's possible to see explicitly that this function satisfies these boundaries. So now let's see what happens with the bold union and the bold intersection. If we consider 2 events without intersection, for example, I measure if the system is in the state alpha plus plus or alpha, if I measure alpha plus plus or alpha plus minus when measuring the observable C, then the probability is the sum of the two probabilities because the two events do not have intersection, and then I get this expression that looks like the one of the 1 bit because I'm summing for the two possible eigenvalues of the second bit. But then this means that the bold intersection is 0, and that the bold union is exactly this probability computed here. So this is my conclusion. We did also the Q-treat. I tell you that it's much more complicated than this, but I wanted to concentrate on the concepts here. So that's why I haven't, it is in the paper if somebody wants to see it. So we have seen the relation between quantum logics and fuzzy logics. It has been clarified. Fuzzy logics can represent perfectly the quantum mechanics if the universe of discourse is chosen properly, and if the fuzzy sets are also chosen properly, the family of fuzzy sets are chosen properly. We see that there is not one fuzzy logic. There is one fuzzy logic for every quantum logic. Neither quantum logics nor fuzzy logics can explain why nature picks up the Birkhoff-von logic or why it is true the seventh axiom of Mackay. And this fact has to be postulated. And then, well, we computed the experimental functions of these systems, these examples that we have seen, and clarified this effect on the NOT gate of the experimental function. Okay, see that it's not the same, the NOT gate than the complementation. Okay, so that's all. Thank you very much.